Okay, we'll go ahead and get started. So overall, the scores on the midterm weren't too bad. Probably the biggest things I noticed, I'll admit, problem three was a bit of a trick. It was the one trick I threw in there. The trick to that one is that you were given the equation for the stress intensity factor for an edge crack, and then you were given the equation to take the stress intensity factor and convert it to the strain energy release rate, and then was to give you your G equation, and then from there just to proceed as the homework progressed. And for problem four, I don't know. I'll admit, I didn't go through and do all the math. The only thing I can think of is with all those trigonometric functions in there, the only thing I can think of is to remember when you're given numbers to do a trigonometric function, it is in radians. So that's the only thing I can think of that some of you did is you plugged in the values in there, did it straight as degrees, and got some things in there. When you're given just numbers in a trigonometric problem to convert it to you either switch your calculator over to radians or multiply everything by pi over 180 to convert it to degrees. That's the only, I didn't go through the math to check, but it's the only thing I can think of. But as I said, overall, the scores were pretty good. I'm reasonably satisfied. And then you'll, for those of you listening remotely or will be watching the recording, I did pass out a new homework tonight. It's relatively short, but just to keep to keep things going, it's just two problems that will be posted tonight. And the first one, given a little bit of information, and then what I'll want you to do is to compute the plastic zone corrected stress intensity factor using the Irwin's correction and the strip yield model. We covered that, right before the midterm, but it wasn't covered on the midterm. So I want to see the equations. I don't want to just see a table. I want to see the equations and a little bit of the work. And I gave you multiple stress levels to do the computations at, and note that the last stress level is equal to the yield stress. So just keep that in mind when you do some of your calculations, and just a hint for that, if you get something that is a divide by zero or something like that, that's okay. If you end up with infinity values, that's okay. And then the other problem we'll talk about tonight about for elastic plastic analysis, the idea of crack tip opening displacement. We'll talk about that very shortly when we get started and do a couple of calculations with that. So this one will be a really short homework. I'm still giving 2 weeks just because that's the tradition, but I will admit that this one will not take 2 weeks to do. So having just survived the you'll you'll get through that. Plus, for those of you who are taking finite elements, you'll appreciate it because you all have the midterm on Thursday. Plus, your homework for finite element, which you'll get right after the midterm. That one will be a bit more extensive, but we'll talk about that more in a couple weeks. So anyway, any questions about administrative type of stuff? And oh yeah, in the syllabus, it said that next week was potentially going to be a remote or canceled class. The trip I was going to take is cancel. The trip I was going to take next week was canceled, so we will have class as normal next week. So, any questions on administrative stuff? Okay. So, if not, come on. So what we're going to do, and I'm going to try to get through this week and next week, possibly just a little bit into the third week, but not nowhere near as long a time as we spent on linear elastic fracture mechanics. but now we're going to talk a little bit, I mean, given the fact that for metals, you do have plasticity and yielding in metals, and with what we talked about a little bit how linear elastic fracture mechanics can be extended to the analysis of incorporating plasticity in metals, but we're now going to spend some time talking about some extensions on that when plasticity is more significant than it was for the limited cases we looked at under the constraints of linear elastic fracture mechanics. So as we talked about, linear elastic fracture mechanics is valid as long as nonlinear material deformation is confined to a small region surrounding the crack tip. And for many materials under high enough loading conditions, it's impractical to use linear elastic fracture mechanics to characterize the fracture behavior. Thus, alternative models are required. So what we're talking about here is we're talking about nonlinear behavior, but time independent, i.e. under the constraints that satisfy the rules for classical plasticity. We're not going to go in viscoelasticity or viscoplasticity type of approaches. And we're going to talk about two elastic-plastic parameters. We'll talk about the crack tip opening displacement and the J contour integral. So both of these parameters describe crack tip conditions in elastic plastic materials, and each can be used as a fracture criteria. And one of the other important things we talked about, if you're defining something as a fracture criteria, you want it to be closer to a material property and less of a geometry dependent problem. So both of these values give nearly size independent measures of fracture toughness, even for relatively large amounts of crack tip plasticities. And like the other methods we talked about, there are limits to the applicability of these two methods, but they're much less restrictive than the requirements for linear elastic fracture mechanics. So to get started, a researcher named Wells attempted to measure K1C values using linear elastic fracture mechanics for a number of structural steels. And he found that these materials were too tough to be characterized by linear elastic fracture mechanics. And what these experiments found is that the existing fracture mechanics theory didn't work for many types of materials. Specifically, when these materials that he tested were subjected to significant plasticity under the load levels that were applied. So when he examined the test specimens, Wells noted that unlike the sharp crack, which is typical for linear elastic fracture mechanics, he observed a blunt crack where the cracked faces had moved apart prior to fracture, and you have the top and the bottom of the blunt crack separated by this distance delta, which is what is referred to as the crack tip opening displacement. And the amount of this crack tip blunting increased in proportion to the toughness of the material. So Wells proposed this opening at the crack tip as a measure of fracture toughness, and today it's known as the crack tip opening displacement, or CTOD. And in his original paper, Wells performed an approximate analysis that related this crack tip opening displacement to the stress intensity factor in the limit of small scale yielding. So what we'll do, start off to do some calculations. We're going to consider a crack with still a relatively small plastic zone, as shown here. So we have our blunted crack, and we have this small area of plasticity, surrounding the crack. And Irwin postulated that the crack tip plasticity makes the crack behave as if it was slightly longer. So we talked about before when we talked about the Irwin correction for the plastic zone, and we defined this radius of this plastic zone around the crack. And therefore, the crack tip opening displacement, this U sub y, can be estimated by solving for the displacement at the original displacement of the physical crack tip reflected, right here. So we have our physical blunted crack tip, and we have this artificial extended equal to our crack length A plus this Ry, the radius of our plastic zone. So from earlier discussions on displacement fields, and we had that table where we gave the displacement fields under mode 1 loading, we can utilize this displacement Ry, be the radius of the plastic zone behind the crack tip is given as follows. So we can say that this Uy, and this Uy here is just the distance from the center line of our crack to the top of the blunted crack. So as we'll talk about in a minute, our crack tip opening displacement is twice this U sub y. But from one of our tables, we could say that U sub y is equal to kappa plus 1 over 2 mu, where kappa is related to Poisson ratios, mu is the shear modulus, times the mode 1 stress intensity factor times the square root of the crack tip, the radius of the plastic zone divided by 2 times pi. And we talked about this before. If you apply some definitions of these parameters, and this cap is a function of Poisson's ratio, and it's different for plane strain and plane stress, it comes to be equal to 4 divided by E prime, where for the case of plane stress, E prime is just equal to the modulus. For the case of plane strain, it has a Poisson ratio term running around there, multiplied by the mode 1 stress intensity factor times the square root of the radius of the plastic zone divided by 2 pi. So we can compute this Ry. So we compute this displacement, and this is all for the case of right in front of the crack. So any theta terms are set equal to 0, which is what allowed us to simplify, because if you looked in the original table, there were angle terms running around in there. So we just set the angle equal to 0, and that's what makes this a lot simpler. And we talked about that the Irwin plastic zone correction for plane stress, this Ry is equal to 1 over 2 times pi times K1 over the yield stress, all this squared. So if we take this and substitute it in for Ry here, and we do a little bit of algebra, we get that our crack tip opening displacement, which is equal to 2 times this Uy, is equal to 4 over pi times K1 squared divided by the yield stress multiplied by the modulus. And then alternatively, using the relationship between stress intensity factor and strain energy release rate, we can also say that this delta is equal to 4 divided by pi times the strain energy release rate divided by the yield stress. Okay? So in the limit of relatively small scale yielding, the crack tip opening displacement is related to the strain energy release rate and the stress intensity factor. And Wells postulated that the CTOD is an appropriate crack tip characterizing parameter when linear elastic fracture mechanics is no longer valid. And we'll dive into this a bit more. And this assumption was shown to be correct when a unique relationship between the crack tip opening displacement and the J integral that we'll talk about later was established. So this is based on the Irwin model. Now, the Strittnield model provides an alternative means of analyzing the crack tip opening displacement. Remember a couple of weeks ago when we talked about accounting for plastic zone corrections, there were two basic ideas. There was the Irwin plastic zone correction, and then also there was the strip yield model, which basically said we applied these artificial stresses to close up cracks to account for the effects of plasticity. So the plastic zone was modeled by these closure stresses applied with the magnitude of the yield stress, which served to artificially close the cracks to account for the effects of plasticity. And the size of the strip yield zone we talked about was defined by the requirement of finite stresses at the crack tip. It was this idea that under classic linear elastic fracture mechanics, you have that singularity at the crack tip because the stresses you multiply things by 1 over the square root of the radius. Well, when the radius equals to 0, things blow up. So thus you have the singularity in there. So the idea of the strip yield model was to allow for finite stresses at the crack tip, which are accounted for due to plasticity, because once your stresses hit the yield stress, then your stresses around the crack tips just stay constant at the yield stress. So here we define our crack tip opening displacement as the crack opening displacement at the end of our strip yield zone. So at the edge of our strip yield zone, we take our displacement between the top and bottom faces of the crack there, and we call that our crack tip opening displacement. So according to this definition, and the derivation of this is more complicated to go into here. It's in the appendix in the book if you're real interested in complex variable analysis and go through. But what you end up with is you get your crack tip opening displacement is 8 times the yield stress times the crack length divided by pi times the modulus times the natural log of the secant of pi over 2 times the stress, applied stress divided by the yield stress. Now, natural logs and secants are tricky functions to work with. So a way to make things a little easier is that if you take this natural log secant term and you do a Taylor series expansion, what you end up with is delta is equal to 8 times the yield stress times the crack length divided by pi times the modulus times 1/2 of pi over 2 times the stress over the yield stress squared plus 1/12 times pi over 2 times the stress over the yield stress to the 4th power plus going forward. So if you neglect high order terms, you basically get rid of everything beyond this first term, and you end up with then just after a little bit of algebra, you end up with the crack tip opening displacement is equal to the square of the square intensity factor divided by the yield stress times the modulus, which is equal to strain energy release rate divided by the yield stress. And if you take this equation and compare it to what we did with the Irwin, it is pretty close. The only difference is for the Irwin, you have this 4 over pi term. You have this 4 over pi term running around in here, but otherwise and since pi's a little over 3, 4 over 3, so you get close to the same results for both of the methods. Now, one thing to keep in mind is that the strip yield model assumes plane stress conditions and a non-hardening material. So under plane stress and a material that you load to the yields, that you load to the yield stress, and then it just continues on at the yield stress. And the actual relationship between the crack tip opening displacement and the stress intensity factor and the strain energy release rate depends on the stress state and the strain hardening. So there is a more general expression that says that the crack tip opening displacement is equal to the square of the energy release rate with some non-dimensional parameter in here multiplied by the yield stress multiplied by this E prime, which is different for plane stress or plane strain, which is equal to the strain energy release rate divided by this M term times the yield stress. So M's a dimensionless constant that's approximately 1 for plane stress, approximately 2 for plane strain. And if your stress state is somewhere between plane stress and plane strain, then this M term is somewhere in the middle. But it's just a way to take this expression and make it more generalizable for non-idealized loading conditions. Now, like anything else, this was based on early work. So just to briefly talk about, there have been some alternative definitions of crack tip opening displacement that have been developed. And two of the more common definitions, at least common according to the book that used, are illustrated in the figure below. First, you have the original crack tip, and you'd say where your original crack tip was just at a sharp crack, and you measure the crack tip open. You measure once you apply more load and it goes plastic, you get this blunting of the tip. So you measure the crack tip opening displacement at the point of where your original sharp crack was located. And then another method that was developed was if you take the point of your crack and you basically set it up so equal 90 degrees from that point, and where this 90-degree lines intersect the top and bottom of your crack, you take that point and you do that measurement of the crack tip opening displacement. And paper by Rice said that for finite element measurements, this is potentially a good way of measuring crack tip opening displacement based on a finite element analysis. And an important point to note is that if your crack blunts into a semicircle, then these two definitions give you the same thing just by the behavior of a circle. Okay. Now how you measure the laboratory. In a few weeks, we'll be going into more detail about how to actually, some of the issues involved in actually doing experimental measurements of some of these parameters that we talked about. But just as an idea, most laboratory measurements of crack tip opening displacement been made on edge crack specimens that are loaded in 3-point bending. So as kind of demonstrated in this figure here. So you have your edge crack, you apply 3-point loading. So you So you apply your load, and then you have constraint rollers, so that's 3-point bending. So this is one of the classic ways of measuring crack tip opening displacements. And early experiments used a paddle-shaped displacement and strain gauge that was inserted into the crack. And as the crack opened, the paddle gauge rotated and a single signal was sent to a plotter. However, this method was inaccurate because, unlike this cartoon here, normally your cracks aren't that big, aren't that wide, so it's difficult to get a real physical strain gauge to the tip of the crack. So nowadays, how we measure the crack tip opening displacement, which is related to this opening V, this displacement V at the crack mouth, and we measure this opening at the crack mouth and use that to compute our crack tip opening displacement at the edge of the crack. And what we do is we assume that each of these specimen halves are rigid and they rotate around a hinge point, as shown in this figure here. So from this figure, we can look at the various dimensions that were given that I admit are kind of hidden by some of my circles, and you can do a similar triangles analysis where you take one triangles to be this big. Excuse me. So you take this big triangle and you use similar triangle arguments that you learned in basic trigonometry, and you relate it to this little triangle here. And so you do a similar triangles type of thing, and you can say that delta over this dimension r times w minus a is equal to the displacement V over R times W minus A plus A. And just to relate that, in just a second, I'm going to this, this, this. Okay, this should help. So from that equation, we defined A is our crack length, delta is our crack tip opening displacement, and the W is the width. W is the width, and then this R times W minus A defines the distance from the edge of the crack to our hinge point. So what we can say is delta, this horizontal dimension, is to the side, the length of the side of this little triangle here, which is R times W minus A, is related to, for a big triangle, V is the base of the big triangle, and the length of the sides is our length A plus this R times W minus A. So that's how we set up our similar triangles for that analysis. So we can take this equation and we can rearrange it to get that our delta, our crack tip opening displacement, is equal to R times W minus A times that displacement V over R times W minus A plus A. So that's how we can compute the crack tip opening displacement based on a realistic experiment. Now, this hinge model is inaccurate when the displacements are primarily elastic because it's based on the idea that you have a blunted crack tip, and if your displacements are primarily elastic, then you just have the blunt crack tip, and this area here would be very small. So what we have to do is so standard methods typically adopt a modified hinge model in which we take the displacements and we separate them into elastic and plastic components, and we only apply our hinge assumption to our plastic displacements. So this figure here illustrates a typical load versus displacement curve that we get from that test that I just showed. So what you do is you do similar ideas. Once you hit a certain point, you do an unload with the slope equal to your initial slope here if your load displacement curve, and you assume that this amount of displacement is your displacement due to plastic deformation. And it's the same type of idea how you measure a plastic strain, that you do a stress strain curve and it gets nonlinear, and then when you unload it, it unloads with the initial elastic modulus, and you say that your plastic strain is just your total strain minus your elastic strain, and your total strain is permanent. It's the same type of idea with a load displacement analysis from this type of test. And the assumption is that this dashed line represents the path of unloading for the specimen, and it's assumed that the crack doesn't grow during the test, that as we apply higher loads, we're haven't gotten to the load level yet where we'd cause an extension of the crack, and all we're doing is that we're extending these displacements here as we apply a higher load. Yeah. So we can estimate our crack tip opening displacement by saying that our delta is equal to our elastic plus our plastic. So it's the elastic part is just K1 squared with our correction factor due to non-idealized loading times E prime plus our RP times W minus A times VP divided by RP times W minus A plus A. So to explain this, so the subscripts EL and P denote elastic and plastic components respectively, and to compute this elastic stress intensity factor, you just use the various take the load and specimen dimensions and plug it into the earlier tables, and for typical materials and specimens, setting this plastic radius is equal to 0.44 has been found to be a reasonable approximation. Again, may not be perfect, but for many materials and test specimens, it's reasonable. And this VP computed the way we talked about here. We do this load and unload and determine our plastic crack tip opening displacement, and and for linear elastic conditions, this equation does well. For linear elastic conditions, it reduces to the small scale yielding result, and when the crack tip, when the real displacement V that we measured is close to this V sub P, then this plastic term dominates. So if it's primarily elastic, it is primarily this. If it's primarily plastic, it's this. And if you have somewhere in the middle, that's where you add in the components. Okay. So yeah, that's it. And that's it. So that's what we have for now for the crack tip opening displacement. So the next thing we'll talk about is the J contour integral. And this J contour integrals enjoyed a lot of success as a characterizing parameter for nonlinear materials. And one of the tricks with this is that in this, even though you have a nonlinear stress strain curve, the assumption for the J integral is that this nonlinear material response is due to the material being nonlinear elastic and not elastic plastic. So if you have a nonlinear elastic material, you'll load your stress strain curve, but then once you unload it, if it's a plastic material, it unloads with the slope here equal to the initial Young's modulus of the material. If it's a nonlinear elastic material, it just progresses back along the loading curve. And if you have zero stress, you're back to zero strain. And you making the nonlinear elastic assumption just simplifies things in terms of setting things up and applying the methodology. So, and the other advantage of using a nonlinear elastic material is that for an elastic material, linear or nonlinear, there's a unique relationship between the stress and the strain. But in an elastic plastic material, it matters how you get there. If you apply a tension test, if you apply a tension load and then a torsion load and end up with the same stress level, but then for another material, you apply a torsion load first and then a tension load, even though your stress levels are the same, the plastic strains you have could be very different. So if you have unloading of the material, cyclic loading, or you have a multi-axial stress state where your loads are applied differently, the stress and the strain aren't uniquely related. It's what's called path dependent, in that your plastic strain depends on how you get there, not just at the stress that you have. So as a result of that, it makes it much easier to analyze a nonlinear elastic material than a material that exhibits irreversible plasticity. So as long as if you change the stress states monotonically in this figure here, the mechanical response of the two materials is identical. And when the problem is generalized to 3 dimensions with various forms of multi-axial stress states, it doesn't necessarily follow that the loading behavior of the nonlinear elastic and elastic plastic materials are identical, but there are many instances where this is a reasonable assumption. So the key to this, assuming a nonlinear elastic material is okay, but you can't account for any unloading, because if you unload in a real plastic material, it'll unload plastically ultimately till you get to here, where a nonlinear elastic material would assume that you just follow your loading path down. So if all you're doing is applying loading and no unloading, this assumption's okay. But if you start, whoops, yeah. Now, if you start wanting to account for not unloading in your analysis, then you can run into issues. And this is also an older theory of plasticity, not used much anymore, not much of any anymore, called the deformation theory of plasticity, which relates total strains to stresses in the materials equivalent to nonlinear elasticity. But Rice applied this deformation plasticity or nonlinear elasticity to the analysis of a crack in a nonlinear material. And through that, he showed that he defined a nonlinear energy release rate, J, which can be written as a path-independent line integral. And Hutchinson, as well as Rice and Rosengren, also showed that this J uniquely characterizes the crack tip stresses and strains in nonlinear materials. So we'll talk about both. So the J integral can be viewed as both an energy parameter and a stress intensity parameter. So the first thing we'll talk about is looking at the J integral as a nonlinear energy release rate. So Rice presented a path-independent contour integral for the analysis of cracks. And he showed that the value of this integral, which he called J, is equal to the energy release rate in a nonlinear elastic body that contains a crack. And we're going to talk about the energy release rate interpretation first because it's closely related to ideas that we talked about before. So we're going to outline the process in just a second, and it can be shown that this line integral is equivalent to the energy release rate in nonlinear elastic materials. So what we're going to do is we're going to take an idea that we talked about previously, and when we talked about the energy release rate for linear materials, what we're going to say is that instead of the linear energy release rate G, we're going to say the nonlinear energy release rate J is equal to the negative of the derivative of the potential energy with respect to the crack area. And the potential energy then is given as follows. So the potential energy is equal to the strain energy stored in the body minus the work done by external forces. This is identical to what we talked about before. So we're going to look again at our crack plate with exhibits a nonlinear load displacement curve. We looked at this configuration before, which allows us to do load control and displacement controlled loading to the plate. And this is a figure we did before, only now instead of linear load displacement curve, we're now accounting for a nonlinear load displacement curve. So we have our original load displacement curve here. Then when we apply changes in load or displacement, we have a modified load displacement curve. And where it was linear before, now it's nonlinear. And if the plate has a unit thickness, the crack area is just equal to this crack length if we have a unit thickness. But it's important to remember that the energy release rate is defined in terms of the crack area and not the crack length. And where this is important is that if you compute the J, this linear or nonlinear strain energy release rate for configurations other than edge crack, like shown here. So for a through crack, you have that the increment in area is 2 times the increment in the crack length to account for the fact that you have cracks on the left end, and then you'd also have cracks at the right end. And for a penny-shaped crack, which is cylindrical, you have your change in crack area is 2 times pi times your crack length, which serves as a radius, times your change in length. So just to note that some of the specifics of what we showed here are valid for the case of the edge crack for the example of what we're looking at, but may not be. You have to modify it a little bit if you're looking at different crack geometries and interpretations. And that's what we just talked about. So for load control, first we're going to look at the case of load control. So we go back to this figure, we're applying a defined load and letting the displacement do what it will. So for that case, our potential energy is equal to our strain energy minus our applied load multiplied by the resulting displacement, which we're going to define as the negative of a which we're going to define as the negative of a complementary strain energy, and thus we can say that this complementary strain energy is equal to the integral from 0 to our load of our displacement multiplied by our increment in loading. And for the case, so if our plate is in load control, we can also say that our nonlinear strain energy release rate is equal to the derivative of this complementary strain energy U star with respect to the crack length, where the load is what's controlled. And then conversely, if we have a fixed displacement, then we have a fixed displacement here we don't apply the load, we just apply a specified displacement. And for that case, we can say that our nonlinear strain energy release rate is equal to negative of the derivative of our strain energy with respect to the crack length for the case of the specified displacement. So what we have is if we look here, our change in strain energy, this du star for load control is different, is just equal and opposite to our change in strain energy from displacement control, and the difference here, the difference here is just the area of this little triangle, which is 1/2 of dp times d delta. So this little triangle here represents the change in the strain energy if you do displacement controlled versus load control. And normally for most materials, this dp times d delta will be pretty small. So what we can say from this is that the J nonlinear strain energy release rate for load control is equal to the strain energy release rate for displacement control. And if you think back several weeks ago when we looked at the same problem for the case of the linear strain energy release rate, we got the same type of thing. So with all that, it's about 5 after 6 now, so we'll go ahead and take our break. We'll get back up at 1/4 after 6, and then we'll use these results to ultimately do some specific calculations for the nonlinear strain energy release rate. Come back in about Okay, we'll go ahead and get started. So with all these definitions, so we can write the detailed definition, and substituting in some of these expressions that we talked about, we can write the detailed expressions for the nonlinear strain energy release rate. So we can say that for the case of load control, that the J is equal to the derivative with respect to the crack length of the integral from 0 to P of delta dP for the case of constant loading, which is just equal to the integral of from 0 to P of the derivative of the displacement with respect to our crack length for the case of constant loading, and integrate with respect to the load. Or conversely, for the case of displacement controlled loading, we can say that it's equal to the negative of the derivative with respect to the crack length, integral from 0 to our applied displacement of P d delta, which is equal to negative from the integral from 0 to delta of the derivative of the load with respect to the crack length for the case of constant displacement. And if you take this equation, do integrate it by parts, and you go through a rigorous proof, you can find what we already talked about, similar to for the case of linear, that the J integral is the same whether you have load control or a displacement control. So the nonlinear, so the J nonlinear strain energy release rate is a more general version of the energy release rate. And for the special case of a linear elastic material, it's just equal to the G term that we talked about before. And just like we talked about before, you can say that the nonlinear strain energy release rate is equal to the square of our mode 1 stress intensity factor divided by E prime, where remember E prime is just the modulus for plane stress, or a Poisson ratio term for plane strain. And this is for the case of mode 1 loading, and for mixed mode loading, you use the equivalent types of terms that we talked about when we talked about linear elastic fracture mechanics for the case of mixed mode loading. Now, there is a word of caution that you need to apply when applying the J to elastic plastic materials, that the energy release rate, you normally think of it as the potential energy that's released from a structure when the crack grows in elastic material. But when you have an elastic plastic material, when you absorb strain energy, you don't recover it when the crack grows or the specimen is unloaded. If you have this plastic zone, some of your energy goes into plastic deformation, and you don't recover it when you unload. So the energy release rate has a somewhat different interpretation for elastic plastic materials. So instead of defining the energy release rate as the energy released from the body when the crack grows, because for the case of a plastic material, not all the energy is released. The J integral definition relates J to the difference in energy absorbed by specimens with neighboring crack sizes. And this distinction is important when the crack grows. But this energy release rate definition of J is still useful when applied in appropriate manners. We'll talk about a little bit later to measure J experimentally, this idea of the energy release rate is still useful. So now we're going to move into kind of a secondary type of definition for the J integral, and that is as a path-independent line variable. So we're going to set up an arbitrary counterclockwise path around the tip of a crack as we show here, and this is a purely arbitrary path. We just, as long as we start at the bottom and end up at the top. And for this case, we can say that J is equal to the integral over our path of W, which is the strain energy density, times dy, and we define our x and y coordinates here, minus traction, which we'll talk about in a second, the derivative of the displacement with respect to the x direction, and we're integrating and multiplied by this increment ds, where this ds, as shown here, is just the increment along the contour that we defined. So we can define our strain energy density, and we can say that our strain energy density is equal to the integral from 0 to our applied strain of our stress multiplied by our increment in strain, where again sigma is the stress, epsilon is the strain, and kind of the classic definition for the strain energy density. So for our traction, we're taking some point on our contour and we're defining a traction vector. We can define our traction vector at whatever point along the contour. So at any point along the contour, we can construct a free body diagram of the material inside of the contour, and we can say that our traction vector is equal to, and we talked about this a little bit when we talked about elasticity theory, that the traction is equal to the stress multiplied by our normal at a point. So it's the same idea. We take this little point here and we set up our little infinitesimal element here, and we talked about this when we talked about elasticity, that you can relate the tractions to the stresses defined by the normal to our plane. So this is same definition that we talked about, the first, right at the beginning of the course, to relate tractions to stresses. And Rice showed that the value of the J integral is independent of the path of integration around the crack. So J is called a path-independent integral, and it can be found that this definition is equal to the energy release rate, and that means then if you're doing like a finite element analysis, you can use this equation and you can look at your stresses and strains and various points and do that integral around there, and applying the other definitions that we talked about to do all these calculations of strain energy densities, etc., and variations in coordinates and in displacements, and we can use that to compute our strain energy, to compute our nonlinear strain energy release rate. Now, one other way we're going to look at things is we're going to look at J as a stress intensity parameter. So Hutchinson and Rice and Rosengren independently showed that J characterizes crack tip conditions in a nonlinear elastic material. And they assumed a power law relationship between plastic strain and stress. So the equation they used, it's a real simple equation. It's that the strain, and this is the unidirectional version of it, the strain divided by some reference strain is equal to your stress divided by a reference stress plus a material parameter alpha times sigma over this not to the n. So in this equation, this represents the elastic part, this represents the nonlinear, the original elastic part, this is the nonlinear elastic part, and sigma 0 is just a reference stress value. Normally, the sigma 0 is set equal to your unidirectional yield stress, and this epsilon 0 is equal to your sigma 0 divided by E, so your yield stress divided by the modulus, which means that it's the strain at which yield occurs, and alpha and n are just constants. And even though this equation has four constants, sigma 0, epsilon 0, alpha, and n, there are really only two fitting parameters. You have sigma 0, which is normally the yield stress. Epsilon 0 is related to sigma 0. So what you can do is if you have a stress strain curve, and you can do a log, and you do a log plot of the stress versus the plastic strain, and do a least squares type of approach, you can determine alpha and n. So what you have is that you have the plastic strain is equal to alpha times sigma over sigma 0 to the n. So your log of your plastic strain is equal to the log of alpha plus n times the natural log of sigma divided by sigma 0. And then you just take various values of stress and plastic strain, set them up in a table, and do a log, and just do a best fit on this using the various mathematical functions available in Excel or whatever, and you can characterize this. And this equation is known as the Ramberg-Osgood equation, and it's a simplified method that's commonly used to do quick and dirty plasticity analysis. Just as we talked about, the one caution is that it really is a nonlinear elastic analysis, because if you unload, you don't account for the permanent strains that are present in your material. So this is the basic stress-strain relation that was used in this type of analysis. Now, adding in some complexity, Hutchinson, Rice, and Rosengren showed that in order to remain path independent, your stress-strain has to vary as a function of 1 over the radius near the crack tip. So a distance is very close to the crack tip, well within the plastic zone. Elastic strains are small in comparison to the total strain, and the stress strain behavior just reduces to the simple power law. So the sigma over sigma naught part goes away, and all you have is just the power law part of it. So all of these conditions imply the following variations of stress and strain. So you can have that the stress is equal to this parameter K1 divided by the J over R to the 1 over n plus 1 power, and the strains are equal to K2 times J over R to the 1 over n plus 1. And these K1 and K2 are proportionality constants, and you can kind of pick them off of plots and other techniques that we'll talk about a little later. So for a linear elastic material, n is equal to 1. And these two equations just predict a 1 over square root of r singularity, just similar to what we talked about before, and it's consistent with the linear elastic fracture mechanics theory. So the actual stress and strain distributions, you apply appropriate boundary conditions, and you get that your stresses are equal to sigma 0 by the modulus times your j times alpha sigma naught squared in, we'll talk about that in a minute, times your radius, all this to the 1 over n plus 1 power. And likewise, your strains are equal to alpha times sigma 0 divided by E times J divided by alpha sigma naught squared In times R, once again to the 1 over n plus 1 power. Oh yeah, and this is multiplied by stresses as a function of n and theta, and the strains as a function of n and theta. And in these expressions, this In is an integration constant that depends on n, and sigma and epsilon, and these sigma and epsilon terms here are just dimensionless functions of n and the angle that you're looking at. So these parameters depend on the assumed stress state, whether it's plane stress or plane strain, and these equations are called the Hutchinson-Rice and Rosengren singularity, and there's plots that exist for this constant In as a function of n for the case of plane stress or plane strain. So this integration constant you pull off of charts such as this. And then for those variations, and then for these variations with n and theta that we talked about, here, there's charts that exist with the angular variations of the stress, and there's similar types of plots for the strain where you look at your angle, so your angle theta, because as you progress along your path, your angle theta is at different locations, and you have for the n, and you can define your various stress components. And note in the plots that are shown here, it's in polar coordinates and not in the regular Cartesian coordinates that we talk about. You notice here, even the little cartoon here shows that the stresses in terms of radius and angle and not in terms of x and y. So the upshot of all of this is the J integral defines the amplitude of the singularity, just as the stress intensity factor characterizes the amplitude of the linear elastic singularity. So the J term does completely describe the conditions within the plastic zone. So the structure under small-scaled yielding has two singularity-dominated zones. One in the elastic region, where the stress varies as 1 over the square root of the radius, and one in the plastic zone, where the stress varies as r to this negative 1 over n plus 1 power. And this singularity zone often persists long after the period where you have lots of plasticity, and your elastic assumptions are no longer valid. Okay. So as complicated as this was for the case of relatively small strains, we're going to talk just a little bit about what happens when you have larger strains. So the HRR singularity contains the same anomaly as we talked about with linear elastic fracture mechanics, whereas you get closer to the crack tip, your radius gets to 0, they both predict infinite stresses. But the singular field doesn't persist all the way to the crack tip. In real materials, the large strains at the crack tip cause the crack to blunt, which reduces the stress triaxiality locally, and the blunted crack tip is a free surface, because if we have our crack tip here, then it acts as a free surface, so our stresses in this direction have to be zero at a free surface. So this complicated analysis we just went to for the HRR singularity doesn't consider the effects of the blunted crack tip, nor does it take account of the large strains that are present near the crack tip. But all of the analyses we did is based on small strain theory, which is the idea of engineering strain. And when you start getting into larger strains, like many other things in mechanics, the assumptions of small strain theory starts to break down. So just as an example, McMicking and Parks did a crack tip finite element analysis that incorporated large strain theory and finite geometry changes. And if you look at this plot here, it shows a plot of the stress normal to the crack versus the distance from the crack. So we have the HRR singularity, which is this dashed line, and then this solid line here, which was obtained through a finite element analysis. And it's a non-dimensionalized curve, so as long as the plastic zone is still relatively small compared to the specimen dimensions, you are comparing apples to apples. So the solid curve reaches a peak when x times sigma 0 divided by j, this term here, gets to be about 1 and decreases as you start getting closer to the crack tip. And this distance here is about equal to twice of the crack tip opening displacement. So the upshot is that if you get larger strains, when you get within twice the crack tip opening displacement, all that analysis we talked about before with the HRR singularity is not necessarily valid. So it's a caution to give because the stresses are more influenced by the large strains and the crack blunting. So the question comes up, is the J integral a useful fracture criteria when a blunting zone forms at the crack tip? And the answer is similar to the argument that we talked about earlier when we talked about linear elastic fracture mechanics, that as long as there's a region surrounding the crack tip that can be described by all these equations we talked about, the J integral does uniquely characterize crack tip conditions, and the critical value of J is a size-independent measure of fracture toughness. And next week we'll talk about a bit more detail the question of J-controlled fracture, the same way for linear elastic fracture mechanics we talked about K-controlled fracture. So the last thing we'll talk about today is ways to measure this J term in the laboratory. So when material behavior is linear elastic, life's easy. J is equal to G, and G is uniquely related to the stress intensity factor. And we talked all about how to compute the stress intensity factor based on load and crack size. However, for nonlinear materials, computing the J integral is somewhat more difficult. Superposition doesn't apply, and J is not proportional to the applied load. So a simple relationship between J, load, and the crack length is usually not available. Now, one option is to use that line integral definition we talked about to the configuration of interest. And Reed measured the J integral in test panels by attaching a bunch of stress. So he defined a contour. Instead of just measuring it with finite elements, he just picked a contour and he put in a bunch of strain gauges around the crack tip. And come in. So since J is path independent and the choice of contour is arbitrary, he set up the contour in such a way to simplify the calculation of J as much as possible. In the same way with a real experiment, you can also do it with finite element analysis. Therefore, stresses, strains, and displacements can be determined along a contour, and J can be calculated according to the equations that we defined earlier. Now, the contour method for determining J in a lot of cases could also be impractical because if you're doing it with real experiments, you need a bunch of strain gauges and the instrumentation somewhat contour. And the contour method, well, it depends. With modern finite element analysis, it's better, but just to note that there are some additional methods that have been developed that I don't think we'll have a chance to get into for determining J numerically. But in any case, here are some practical experimental approaches that have been developed. For example, Begley and Landis, who were among the first to measure J experimentally, actually used the energy release rate definition idea. So these figures here schematically illustrates their approach. So they took a bunch of test specimens and they used the same size, geometry, material, and what they did is they put in cracks of various lengths as reflected in these various A terms here, A1, A2, A3, A4. And they deformed each specimen and they measured the load versus the displacement. And note here, you have load displacement curves for each of your crack lengths, and the area under each of these curves is the strain energy absorbed by the specimen. So what they then went is from this is at various displacement levels, you can take your area under your curve, so you can define your U for each of the various displacements for each of your crack lengths, and you can do a plot here where you plot your displacement versus crack length for various displacements. So for here, you define a constant displacement and you say for crack length A1 you have this, crack length A2 you have this, crack length A3 you have this, crack length A4 you have that. So that's how you generate this plot. And for an edge crack specimen of thickness B, we can also say that the strain energy release rate is equal to -1/B times the derivative of U with respect to A for our defined displacement. For our defined displacement. So J can also be computed by computing your local. Oh, we're almost done. So we can take at these various points the derivative of U with respect to A from this plot, take that, plug it into this equation, and then we can use that to compute our value of J as a function of displacement for our various crack lengths. And this is a calibration. Now, the trick to this is a relatively straightforward method, but it's a calibration curve. It only works for the specific material, specimen size, specimen geometry, and temperature for which it was obtained. So to do a general definition, you have to take a bunch of specimens and do a bunch of tests and analyze them to determine a general relationship of J for a variety of conditions. And even then, it'll be empirical because you'll basically say, okay, for your real condition, what is the close to the situation that you're looking at, and therefore which of these plots that you use. And just in general, when you're looking at experiments, this is something you always have to be careful about. To what extent are you calibrating to things, and to what extent can you take the results and be predictive? So there is a caution to this. Now, Rice showed that it was possible in certain cases to determine J directly from the load displacement curve of a single specimen. And their derivations of J relationships for several specimen configurations, they utilized an idea called dimensional analysis. So, for example, a double-edged notch tension specimen of unit thickness is shown here, and we do cracks on opposite sides of the panel separated by a distance defined as 2b, and we can define our crack area related to the crack length and the distance between the cracks. And for this, we modify the definitions, and we say that J is equal to 1/2 the integral of 0 to p of the derivative of our displacement with respect to our crack length for the case of constant load, integrate over the load, which is also equal to negative 1/2 of the integral from 0 to p of derivative of delta with respect to B, constant load, dp. So we modified our J integral definition for this case, just to take into account the crack length and the distance between the cracks. And to compute J from this expression, you need to determine the relationship between load, displacement, and panel dimensions. So what you can do is to compute J from here, you can assume an isotropic material that obeys the Ramberg-Osgood stress-strain law. So you can say that your displacement delta is equal to your half the distance between the cracks multiplied by some dimensionless function. It's a function of P over sigma 0 B, A over B, sigma 0 over E, Poisson ratio, alpha, and N. So for fixed material properties, we only need to look at load and specimen dimensions. So load and specimen dimensions. So we can say that our delta is equal to the delta due to elastic analysis plus our delta due to plastic analysis. And we take this expression and we substitute it into these expressions. And what we get is that J is equal to negative 1/2 integral 0 to P of the derivative of the elastic part of the displacement with respect to B for constant load plus the derivative of the plastic part of the displacement with respect to B constant load times dP. And you can do the math and you can derive that it's equal to the square of the stress intensity factor over E prime minus 1/2 the integral of 0 to P of derivative of the delta P with respect to B for the case of constant load integrating over dP. So we only need to be concerned about the plastic displacements because the solution for the elastic components already available. And if the plastic deformation is just confined to this region between the crack tips, which makes sense, we can assume that B is the only length dimension which affects the They have plastic deformation delta P, which is a reasonable assumption provided the panel's deeply notched so that the average stress in the ligament is substantially higher than the remote stress in the gross cross section. So the upshot of all of this is that there are a variety of ways to measure this J term, some of which are more specific, some of which are more generalized, and some are simpler than others. And if I remember right, let me just look real fast. Yeah, yeah, yeah. Later on in a couple weeks, we are going to talk about some specific types of tests that have been developed to measure this J term. Okay. So, anywho, that's it for today. So, depending on where you live, you can get home for a little bit of trick or treating, or more importantly, get home before the bad weather starts moving in. So it looks like in a couple hours the weather's going to get pretty spooky. So anyway, and I'll be posting homework 3 tonight for those of you attending remotely. So with that, have a good week, and I'll see you guys. One moment.